today we're going to jump back into where we left off last week. And then I'm just going to finish up kind of these last two things, and then we're going to have a really cool guest lecture that I think you guys will really enjoy. Okay, so last week we talked about doing falsification, so finding failures of systems. And specifically, last Thursday, we talked about doing falsification using planning techniques. So we talked a lot about tree search, specifically two different types of tree search, heuristic search and Monte Carlo tree search, where heuristic search was a lot of different variations of an algorithm called rapidly exploring random trees. And we left off with Monte Carlo tree search. And so today I just want to dive into kind of these two last things, starting with reinforcement learning. So if we kind of take a step back and think about kind of the high-level approach to what we were doing, or the high-level setup that we have here, is we have this kind of system that we've been testing, and we can think of ourselves kind of testing this system as an adversary for the system. So we're like trying to cause the system to fail. And what the adversary can do is it can give disturbances to the system at each time step. The system then, takes its step, calling that step function we talked about. And then the system can spit back out some reward for the adversary. And so it's kind of weird to think of reward as kind of being a bad thing, but in this case, because it's an adversary, the adversary gets rewarded kind of the worse the situation is. So the closer that the system is to failure, the higher the reward the adversary will get, because the adversary is trying to make it fail. And so this kind of loop here, where you have the system here, you have this adversary, this might look familiar to some of you. And it might specifically remind you of, the answer's kind of already on the slide, it might remind you of reinforcement learning. And so what's really cool, and kind of the key insight here, is that this is exactly the setup that we have for reinforcement learning, where we're trying to train an agent to do some task, and it gets some reward feedback, and it can take some actions. In this case, the actions are disturbances. And we don't call it an agent, we call it an adversary in this class, because we don't want to get it confused with the agent that's in the systems. But the idea here is now we can just take advantage of all of these reinforcement learning algorithms that are out there, using this setup to train an adversary that can cause our system to fail. So I'm not really going to get into what the different reinforcement learning algorithms are. That's obviously another entire course here at Stanford. But what's cool is if we can set our system up in this way, we can just plug in off-the-shelf reinforcement learning algorithms to do this. Why would we want to do this? So what's really cool about this is there's been a ton of research in the field of reinforcement learning over the last couple decades to design reinforcement learning algorithms that are sample efficient. So we want to, do the fewest steps through this loop as we can to learn a good policy or to learn a good adversary. And the entire field of reinforcement learning, a huge focus area, is this kind of sample efficiency. So we can take advantage of all of this research and work that's already been done in that field in order to very efficiently find failures using reinforcement learning, which is pretty cool. Another thing that's cool, that's kind of different from the other algorithms that we saw last week, is that it can generalize to different initial states. So if you remember when we were doing tree search, we kind of started from some initial state, and then we just kind of built a tree out from that. And so we would need to start from a whole bunch of different initial states if we wanted to find failures from different states using tree search. But with reinforcement learning, a lot of these algorithms allow the agent to kind of generalize to a lot of different states, or the adversary to generalize to a lot of different states. And so we can actually just kind of off the bat find failures from a lot of different starting points. Okay, so now I'm going to show an example. So what's going on here is we have our continuum world again. But now instead of just starting from kind of one initial state over here, as we had been for the other part of this lecture, we're going to start from a whole bunch of different initial states. So all of these kind of trajectories here are just trajectories that start from some initial state and then roll out to some path. And our goal is to make all of these trajectories fail. So right now, none of them are actually ending up in the obstacle, so none of them fail. And what we want to do is train a reinforcement learning agent to select disturbances in each of these different states that it's in throughout its trajectory to cause it to run into the obstacle. So when I show this animation, you'll see kind of over time what the training of this reinforcement learning agent looks like, and you'll see that we can kind of progressively train it to produce failures from these different initial states. Okay, cool. So now you see that most of these trajectories, they start from some initial state, and we've trained this adversary to pick disturbances that cause it to move into the obstacle. Okay, and so this is what the training kind of looked like over time. So after, a few training steps, it's still hasn't quite figured it out. But as we, train for longer, the adversary is able to get better and better at causing the system to fail. Yeah?
Sorry, can you clarify what exactly we mean by causing it to fail? Like, is it returning the environment from the agent's perspective, or is it or forcing an agent's hands, or what exactly is it doing?
Yeah, good question. So the question was, can I explain what exactly I mean by causing it to fail? So what's going on here is that loop we had that I showed a few slides ago. This loop here. So at every single time step, the adversary gets to pick a disturbance. So the disturbance is those things we talked about before, where it could be on the agent, it could be on the environment, it could be on the sensor, whatever the disturbances are for the system. At every time step, the agent or the adversary is picking that. So we're basically training an adversary to pick disturbances that should cause the system to fail. Yep. I think we'll just have to watch that cool animation again. Oh, darn. Okay. I can't see it animating on my screen, which is why I always look up there when it's actually moving. Okay, cool. So one last thing here. I think I have found the actual use for the fireworks animation. All right. Okay. So just one more note here. So using MCTS, which is what we talked about last week, and then reinforcement learning to search for the most likely failure of a system is often referred to as a concept that we call adaptive stress testing. So if you've kind of heard that phrase thrown around, all it means is kind of doing what we just did. And typically we associate adaptive stress testing if your objective that you're using. So in that case, maybe the reward for the reinforcement learning agent has some notion of likelihood in it, but in general, it's just when we're trying to find the most likely failure, we call it adaptive stress testing. And Anthony's going to talk a lot more about that today in his guest lecture. But what's kind of cool is that the idea of adaptive stress testing was actually formed in our lab here by a former student named Richie Lee. So you can check out this work if you're interested. And Anthony, again, will talk a lot more about it. Okay, so that's reinforcement learning. And then finally, I just want to briefly touch on simulator requirements, but more generally, I just want to talk about this topic of okay, how do I actually go about picking a falsification method? So we just went over a ton of methods in the last week or so for doing falsification. And so you might be wondering okay, well, how do I decide what to do? And maybe this is also relevant as you're doing the project. What do I even decide what to do? And so there's a lot of considerations here. So one is just kind of a general consideration. It's very domain specific. So some of these algorithms might work really well in one domain and work terribly in another domain. And sometimes you don't know until you just try them out. Another thing to think about is kind of the rarity of failures. So if the failures of your system are not super rare, it's not safety critical, or it's just in one of its initial stages and it's still failing quite often, then it might not be super efficient to go all the way to applying MCTS to find failures, or these big gradient-based optimization to find failures. You might just find the failures by doing that direct sampling that we talked about, kind of that first algorithm we talked about. And in that case, it's probably going to be more efficient because there's no reason to sit down and try to take gradients or do tree search or anything like that if failures are already easy to find. But kind of the more rare these failures get, the more benefit we'll see to using these very sample efficient algorithms like tree search. And then finally, kind of what's shown on this slide, this is a figure that we have in the book. We just want to talk about, so one thing that will already limit you to what falsification methods you use is the type of simulator that you have. So the type of model or simulator that you're using to simulate your system. So for example, suppose we have a simulator that we can put in an initial state and we can put in a sequence of disturbances and we get out, the trajectory that occurred, or maybe its robustness or something like that, but we don't get to see what actually happened in between to generate that trajectory. So maybe, for example, this is a big flight simulator. We don't actually know what's going on under the hood. In that case, then we could use methods like direct sampling, fuzzing, direct methods, population methods, all these methods that don't require gradients. So that's something that could already kind of limit you off the bat. If you can't take the gradient of your system, then you can't use these first order and second order methods. And then furthermore, these kind of reinforcement learning based methods or tree search based methods, they require us to actually be able to take individual steps of our system and stop, see what happened in between, make a new decision, and then take another step. And so if you can't do that with your simulator, if all you get to do is put in one thing and it gives you a whole trajectory, then you're not going to be able to use these types of methods. So this is just kind of a rule of thumb to be thinking about as you pick falsification methods. Yeah?
So could you teach a bit more on the first one? What's the difference between that one and the first category?
Yeah, so the question was, can I talk a little bit more about first order and second order methods? What's the difference between these and the first category? So first order and second order methods, they're a type of method that fits in that local descent category that we talked about last week, where you're basically starting from an initial design point and you're taking steps towards the minimum. And when you do it using first order and second order methods, they require the first and second derivative of the function, or the gradient and the Hessian. And so if you can't compute the gradient and the Hessian, for example, maybe you have like a big flight simulator, it's black box, you don't actually know what's going on inside, you can't compute the gradient of this with respect to this, and so you wouldn't be able to use these first and second order methods. But that said, if you can compute the gradient tends to be a very powerful tool for actually doing this optimization, and so if you can compute the gradient, it's a big plus, because these methods might perform better. Yeah?
Could you remind me again what the difference is between direct sampling and direct methods?
Sure, direct sampling is like, it's that first algorithm we presented, it's like Monte Carlo sampling. We just sample the system a whole bunch of times. Direct methods would be like local descent methods that like take a step, but they don't use gradient information to decide like what step they want to take towards minimum.
Like zero order.
Yeah, exactly, zero order. Yeah, so another name for direct methods is zero order methods. Cool, so that's it for me today. So now I'm super excited to introduce our guest lecturer, who told me not to read his bio for an introduction. So here's Anthony.
Cool. Well, thanks so much for having me. Thank you, Sydney. I feel like one of the worst things that you can possibly do is do a presentation directly after Sydney. So I don't recommend it. Her slides are always amazing. I will do my best. So yeah, thank you for just saying my name. My name is Anthony Corso. I'll give a kind of a short background of who I am. So I did my PhD here at Stanford with Mykel Kochenderfer in Sizzle, and I worked a lot with both Sydney and Robert and Harrison and a bunch of other folks in Sizzle during my time here. And it's a place I love very deeply, so it's a pleasure to be back to be chatting with you all. So after I did my PhD, I graduated in the middle of COVID, which was not maybe the best time to go searching for a job. So I decided to stay on as a postdoc. And I also helped run the Stanford Center for AI Safety for 3 years. I was the executive director. And during my time, both as a PhD student and as a postdoc and running the center, I got to work on a lot of really cool safety critical AI applications. So for example, Sydney and I built a vision-based aircraft collision avoidance system on an exchange trip in Edinburgh. We worked on formal methods for verifying machine learning components, even those that process images. You'll learn a little bit more about formal verification, I think, later in the course, which is quite exciting. And then I worked a lot, especially in my PhD, on the discovery of failures. So using these optimization, falsification approaches, and that's primarily what I'll be talking about today. Being at Stanford, you also get a lot of cool opportunities to work on random things. I worked on a project where we used language models to simulate human war games with a few folks in our lab, as well as at CSAC. Worked on some stuff related to the index report, but basically the big concept that I'm most interested in is how we can use AI for really important safety critical applications. So later on in my postdoc, I actually switched directions a little bit, or picked up some new research topics that really kind of changed the direction of my life, I would say. So Mykel established a really cool collaboration with the folks at the Stanford School of Sustainability, who are thinking a lot about how do we use the Earth's subsurface to support the net zero transition. So we need things like raw materials, we need copper, nickel, lithium, things that go into batteries and infrastructure. We can get renewable energy from the subsurface in terms of geothermal energy production, as well as hydrogen production and storage. And we can also use the subsurface as a place to store carbon. So instead of pumping it out into the atmosphere, if you trap it in sufficient concentrations, you can put it underground and trap it there for a long time. Now, what's cool about these problems is they're very, very challenging decision problems. You have to figure out what to do in order to operate these projects efficiently and safely, but they have a huge amount of uncertainty. So we have no idea what's really underneath the subsurface. It's very difficult to observe. And so applying these sort of AI techniques for understanding what's in the subsurface and how you make good decisions there became sort of the target of my research interests. And then earlier in 2024, in the spring, I started a company called Terra AI, which I'll talk maybe a little bit more about at the end, that basically does this type of work, but in an industrial setting. So with that little intro, let me give you kind of a quick outline of what I want to talk about today. So in the first part of the talk, for maybe 30 minutes or so, we're going to talk about how we use adaptive stress testing in a variety of transportation systems and use it to sort of, in the real world, validating real and complex autonomous systems. Then the second part, I'm going to talk a little bit more about those Earth resource problems that we talked about, demonstrate why those are also safety critical, and maybe float some ideas about things you could think about for your final project or future research directions. Okay, so let's jump in. Oh, and by the way, feel free to stop me at any time for questions or comments or whatever. I want this to be as interactive as possible, so please do so. Okay, so I think when it comes to thinking about using autonomous systems in really safety critical domains, and I personally thought a lot about the possible bad outcomes that could occur, it's always important to remember why we want to do this in the first place. And I think there's a lot of really amazing things that could come from bringing more autonomy into our transportation systems. So aviation already enjoys a very high degree of safety standards, but airspaces are getting more complex, more dense, and we really want to be able to maintain that really high level of safety. And things like the ACAS-X system that Mykel and Robert and Sydney have all worked on has been shown to improve the factor of safety on for collision avoidance by a factor of 3 to 5, which is pretty exciting. Similarly, right now, driving accidents kill over 1 million people every year, and something like 94% of them are just due to human error. So if we could just bring that number down, that could be a huge benefit to the world. But of course there are risks. So you may or may not have already heard about this particular collision that occurred back in 2018. This was sort of considered the first pedestrian fatality due to an autonomous vehicle. It was Uber ATG, which was Uber's self-driving division, which has now since collapsed. They were operating in Arizona, and a woman was crossing the street with her bicycle, and due to a sequence of errors, but primarily due to the system not correctly classifying this person bicycle combination and then poorly predicting where she would be, the vehicle struck and killed her. So there are really, really, really intense real world consequences for operating these types of systems out in the real world. Of course, now we have a lot more autonomy on the roads. So this was actually just from 2 years ago. There were tons and tons of crashes related to the Tesla autopilot feature, which is not fully autonomous, but indeed has led to a number of fatal collisions. And really what's going on here is that these systems are just brittle in the ways that machine learning systems are brittle. So here's someone videotaping in their Tesla, it's seeing a bunch of traffic lights kind of coming at it down the street, and you might wonder what's going on there, and then you see that it's actually a truck transporting traffic lights driving in front of the Tesla. And so it's these types of sort of bizarre edge cases that you can't necessarily predict when you're going to put these things on the road. Okay. Another thing that makes sort of the delivery of safe autonomy out in the world very challenging is that we have very stringent safety requirements in a lot of these domains, as it should be. So in aviation, for example, we might have a specification that says we can't have more than a probability of failure that's higher than 10 to the minus 9 for every 150 seconds of flight time. And so the companies that are building this autonomy have this extra challenge of sort of proving to the regulators that the system they're building is sufficiently safe. And if you do that in simulation, and I think you guys may have talked about this a lecture or two ago, if you need a level of safety at 10 to the minus 9, it's going to require billions and billions of simulations in order for us to gain confidence that we're reaching that level of threshold. How many simulations did you guys run for ACAS-X?
Maybe about 100 billion.
100 billion, yeah. So, and that was using a gigantic supercomputer, and it's tricky. So all of this is to say that if we just take a very naive approach to the kind of safety validation problem, it's going to be very difficult. And so that's why a lot of the research that's been done in this lab and many others has focused on how can you more efficiently find these failure modes of the systems that we wish to deploy. So I want to talk a little bit, and thank you, Sydney, for the introduction of what adaptive stress testing is. So adaptive stress testing is sort of like a fancy term for just doing falsification with the most likely failure objective. So the sort of key insight that was brought about in the original work done by Richie Lee was, instead of just naively searching for failures, let's sort of actively look for those failures using some known optimization techniques like tree search or deep reinforcement learning. And setting up your problem like this. So this should look fairly similar to maybe some things that you've seen before, but the idea being that you have your system under test. This would be like your agent, and it's taking actions in some environment. And then we have an adversary that's perturbing the environment in some way. So maybe that's controlling the noise of the sensors, or it's controlling the behavior of other agents in the environment. And it's doing so with some information about what's happening within the environment. And so when you set it up this way, you can apply those optimization and reinforcement learning algorithms pretty straightforwardly. The other key insight that came in the original work on adaptive stress testing was rather than just looking for any old failure, which actually is sometimes easy to find because you can make really extreme disturbances, maybe you want to look for the most likely failure. So those failures that are still somewhat likely to occur and are not really extreme examples of the types of disturbances that you could apply. So the early work on AST looked something like this. So it's a pretty similar picture, but there's a few slight differences. So they had a simulator. In this case, it was an ACAS-X style collision avoidance system. And it was packaged in sort of a black box simulator that they couldn't get a lot of sort of internal workings of. But what they could do is at each step, they could set the random seed of the simulator. And that random seed would change what the outcome of a probabilistic sampling process was. So they could put in the random seed, and then out would come a transition probability. So basically, if you give a seed, it would tell you how likely that transition was to occur. And then it would also give you some information about, for example, whether or not a collision occurred. That's the rare event that you were looking for. But also a notion of how close the two aircraft were at the point of closest approach. So this can give you kind of a little bit of a signal that you can work off of to inform the optimization. So they put this into a tree search style algorithm, and what came out was very interesting. What came out was the ability to find a fairly large number of near mid-air collisions between two aircraft that were running this collision avoidance system. So here we have sort of a top-down view and a side view, and it basically shows a particular trajectory that occurred, as well as some reversals in the advisory that was given. And these results were really useful to the designers of the system to understand what are those configurations that could lead to failure. Okay, so yeah, please.
One question about this seed that we put for the simulator. Is there any sort of, so I guess on the previous slide, is there any sort of interpretation of that seed, or is it completely, I guess in random generators, we think of the seed as really independent of what comes out, like we can't really interpret it. So I wonder if there's any intuition as to why the reinforcement learner should be able to find good seeds, I guess.
Yeah, great question. So the question was around, is there a way to sort of interpret the seed? The seed is something that's kind of just an input that shouldn't necessarily, two seeds that are close will not necessarily lead to two outcomes that are similar. And so why is it the case that a reinforcement learner might be able to learn something in this case? So it's a great question. The algorithm that was used here was not like a deep reinforcement learning algorithm. It was actually Monte Carlo tree search. And so what Monte Carlo tree search does is it's actually just a pretty efficient way of searching down a branching tree. So you can think of the selection of each seed as a different action, and then it would sort of explore regions of the tree where a few seeds in a row kind of led to a configuration where the aircraft were already getting close, and then it would do some more random sampling. So you can think of it as almost like Monte Carlo sampling, but for parts of the trajectory that are already leading to things that are close to failure. And so it was just an efficient search, yeah.
But in this graph, we won't always know what the terminal tau is if you're supplying a simulator with multiple seeds in a sequence, right?
So at every, so the question is, how do you know when the simulation is over, or when do you get that signal tau? So I believe, and Mykel can correct me, so you're giving a seed that's producing one step, and then the simulator will tell you, was that step terminal or not, or was there a failure?
This is like a Boolean, whether or not it's true.
Yeah,
Okay, great.
correct. Yeah. Great, and yeah.
You said there was a connection between the seed and the transition probability?
Yeah.
Seed informs.
Yeah, so the seed is what sort of determines what the random number generator does, and whatever the random number generator does, it will return to you sort of the probability that that occurred. So occasionally a seed will produce like a very low probability transition, and then most of the time it'll be a higher probability transition. Yeah. And I believe this technique was sort of taken because of these real world requirements that Sydney was just talking about on the simulator itself. It just didn't have sort of an API exposed that allowed you to tweak the things you'd really want to tweak, which are like the sensor noise or the behavior of the other pilots. Okay. So with that kind of like historical background, if you want to call it history, from a few years ago, I want to talk a little bit about where the research in adaptive stress testing has kind of gone since then. And I want to do this by talking about just what are the challenges that come up when you begin trying to apply some of these algorithms into the real world. So I broke it down into three kind of broad categories. The first is the difficulty in specifying the objective. So in some cases, the objective you care about is quite clear. Maybe in collision avoidance, the thing you want to avoid is the two aircraft colliding. On the road, driving, it might be a little less clear. So it might be a collision. You definitely want to avoid that. But it might be other more nuanced things like traffic rules. So this right here is a temporal logic specification for how you should behave at an intersection. And so, you know, don't try to read it. It'll strain your eyes. You can go take a look here. But these specifications can get extremely complex, and you're very likely to miss important things because we probably don't all operate at intersections exactly by the rules of the road. You're doing it based on sort of the cultural norms of the area and things like that. Another challenge, which has been talked about earlier, is just how do you model the environment? So in the driving and transportation domain, this can get super challenging. I'll show some examples of that. And then lastly, how do we optimize in these very complex sort of long time horizon environments? So I'll show you a few sort of examples of how we address some of these problems. So let's start by talking about specifying the problems. So pretty shortly after Richie did his work showing this adaptive stress testing approach working in the aviation sector, we started thinking about how we might apply this in the driving sector. There was a lot of interest in ensuring the safety of these systems as they were beginning to be tested on the road. So we set up a pretty simple kind of scenario where you have a pedestrian that's walking across the street, and we have our agent being a vehicle that has some simple policy that it should just sort of stop for the pedestrian if it observes it. But then we said, okay, there's some noise, there's some disturbances that could occur in the environment. So number one, the pedestrian could not choose to walk in a straight line at constant velocity. So there's some maybe variation in how the pedestrian behaves. Additionally, the vehicle is not going to necessarily sense the pedestrian exactly accurately in terms of localizing where they are in space. So we specified those as the disturbances, the behavior of the pedestrian and the sensor noise. And we wrote what we thought was a pretty fancy reward function. So we said, okay, we're gonna give a penalty for not finding a failure. We're gonna have a heuristic about how close the vehicle and the pedestrian were because that's what Richie did and that worked really well. And we're gonna penalize rare actions so that we try to find this sort of most likely failure outcome. And then we threw some solvers at it, MCTS and DeepRL. So we did that, and the results were this. So we'll let it replay. But basically, the vehicle sort of correctly identifies the pedestrian, comes to a safe stop, and the pedestrian runs headlong into the vehicle. And so what went wrong here? Well, first of all, what went wrong is that we didn't necessarily specify our objective correctly. So we just said that a failure occurs only when the two sort of objects come into contact, and not that, say, for example, the vehicle was at fault for the collision, which might have been something that we care about. Also, we might have had an oversimplified model of how pedestrians behave, although people have shown me videos of people doing this very thing for insurance fraud after showing this video. So maybe it's something we should worry about. So the idea here then is, okay, how can we kind of modify our specification, or at least change the sort of the objective function that we're optimizing for in order to account for some of these more nuanced things that we might care about. In this particular work, we pulled from a concept called responsibility sensitive safety. So this is an effort to basically codify a lot of the rules of safe driving. So like rules of the road codified as very specific mathematical specifications. And they kind of took these like high level things like don't hit someone from behind, don't cut in recklessly, and they sort of formalized them in this mathematical way. And then they sort of used it as a way to kind of identify in certain situations who is at fault and sort of how you should have behaved in order to sort of drive safely. So they were thinking of this as sort of a way that you could like write down the rules of the road. I don't think that was ever really going to quite work, but it is a very useful tool in order to evaluate certain scenarios and see who was at fault. So the key idea is that we took those statements and we used them to evaluate the safety and the responsibility of each party involved in the collision. And so you can see here the trajectory that occurred with the vehicle and the pedestrian. And basically what we determined from this is that while the kind of situation was dangerous in the sense that there could have been a collision, the response of the vehicle was quote unquote proper. So it applied the correct braking and it actually came to a complete stop prior to the collision. So the key idea here is let's change our objective to search for failures where the autonomous vehicle itself is to blame and that we're not in this situation right here. So if we change our objective and run the optimization again, we get a situation that looks something like this. So now the most likely failure that emerges is one in which the pedestrian has this kind of sort of diagonal walk, which is actually quite similar to the Uber ATG collision. And the sensor noise is sort of amplified in a biased way such that the vehicle thinks the pedestrian is actually still on the sidewalk. And the result is a collision. So it's using these techniques that you can kind of find much more relevant or at-fault failure modes for autonomous driving. Okay, so let me pause there for a second and see if there are questions. Yeah.
What confuses me a little bit when we talk about amplifying sensor noise and then biasing in a certain direction, how much of that is really just searching for a failure and how much are we biasing our whole system model in a sense and like changing the system model?
Yeah, so the question is, when we're talking about the resulting bias in the observations here, sort of how does that come about? And what's going on here is that we have a model of the sensor noise that maybe you learned from some data, so you understand like what are the range of noises that you might expect. And in the nominal operation, which you see here, that sensor noise actually is being applied, and it's sort of uniformly distributed with the zero mean and whatnot. And so what the adaptive stress testing is doing is basically just finding sequences of sensor noise that lead to failure. And it just so happens that the failures occur when the sensor noise is biased. So like it just finds those outcomes because a failure only occurs if the car thinks the pedestrian's on the sidewalk, and that only occurs if there's sort of a negative bias to the thing. And so it's able to sort of tease out those types of relationships and give you those trajectories. Now, this doesn't mean that the sensor noise that's going to be experienced in the real world is biased. It just tells the engineer who's building the system, hey, be careful about this particular situation, maybe learn from it. Does that answer your question? Yeah. Yeah.
To what extent do you think you could modify these kind of procedures to be more scalable? I guess because here you sort of have to design the reward function and the scenario like one like hand in hand.
Yeah.
How would you sort of do it for like multiple scenarios? Do you really have to start from scratch every time you want to test a different scenario for like pedestrian interaction? Yeah,
that's a great question. I don't have these in backup. So Robert's actually done some very nice work on that he can maybe share with you offline of basically developing a broader framework for this type of approach. So they've sort of pre-selected, I think like 10 different sort of types of scenarios that are common, and then different configurations and initial conditions of those scenarios, and then search for failures across all of them. And the trick is basically finding, well, first of all, like being able to create a bunch of scenarios in sort of a generative fashion so that you don't have to like hand design these things, and you can do that. I mean, these days people are probably doing in-context LLM type stuff, but then, it was sort of like finding frameworks that were useful for specifying these types of scenarios and generating them automatically. And then it's also about finding objectives that are allow you to kind of solve for relevant failures in each of those. And a lot of these things like responsibility, sensitive safety, like actually do apply for a wide range of scenarios. We just kind of pulled the minimum set that was useful for this particular scenario, but you could imagine scaling that up and using the same technique for a lot of different scenarios. But yeah, it's a great question, and it's a big engineering effort to get that to happen. Cool. Other questions? Okay, great. Okay, so let's talk about the second kind of set of challenges for adaptive stress testing. And I'm not going to linger on this too much because I think this was already covered to some extent in lecture, which is how do you actually model the environment in such a way that it's sort of realistic to the operational environment that you intend your system to operate within. So the challenges here, especially in the driving context, are twofold. So number one, human behavior on the road is incredibly complex. So if you think about the problem of like saying, hey, I want to evaluate my self-driving car policy in simulation, and I want to create a bunch of other agents on the road that like behave like other drivers would. Well, creating agents that behave like other drivers would is exactly as hard a problem as building a self-driving car itself, right? So you need a way to sort of like mimic this behavior without necessarily going full bore and creating a bunch of autonomous vehicles on the road. And that can get very tricky. Also, the sensors that the vehicles use are not so simple, right? So we have LiDAR sensors, we have camera sensors. These are very, very high dimensional and tricky sensors to sort of model. So if you want to try to capture like what is the noise distribution in a sensor, it has to sort of respect the what is true about LiDAR, for example, and that can get very complicated. As opposed to something like maybe GPS, which has like a much more well-characterized error distribution and things like that. Okay, so what do people do? So people generally try to model the environment from data. So this should be familiar, thinking about getting some samples of your environment either from the real world or through simulation, and then learning models from those samples. And there are a lot of cool data sets out there for driving in particular, where, for example, maybe they flew a drone over a highway and they sort of record with a camera all of the different vehicles interacting on the highway, and then they do some sort of automated segmentation and object detection to figure out who's who and then how they're behaving over time. And the result is like you basically get a data set with a bunch of trajectories of what other agents are doing on the road. Additionally, they can get this information from like fixed cameras, and importantly, there's data sets where they kind of observe the interactions through intersections where things can get very complex and people are kind of interacting in very sophisticated ways. Now, what do you do with that data? Well, you can build all sorts of models, but one of the types of models that has been pretty effective for sort of imitating real-world data are deep generative models. And that's obviously even way more present now with large language models and diffusion models, but at the time that a lot of this work was done, the best model for this were generative adversarial networks, which are deep generative models that sort of play this zero-sum game where a generator tries to produce realistic images that look like the data you've provided it, and a discriminator tries to figure out which are real and which are fake. And the result is that you sort of learn these a generator that's able to produce, in this case, handwritten digits from the MNIST dataset. Now, versions of GANs have been applied in a lot of domains. One of them is actually modeling the sequential behavior of multiple agents on the road. So this was some work out of Sizzle as well that took one of these data sets and sort of began learning models of how drivers interact on the highway. As you can watch the little vehicles drive around, these are all from the learned policy, and you can see they sort of like cause each other to brake when the one in front brakes, and you get kind of realistic looking traffic behavior. And this is a really useful model for when you want to evaluate your system on a highway, for example. You can also use these same types of deep generative models for modeling sort of the sensor dynamics that you might observe as an autonomous vehicle. So actually this one on the right here is from Sydney and myself and others where we trained a GAN to sort of look like the images that an aircraft might see when it's taxiing down a runway, for example. And I'll talk a little bit more about this specific example in a few moments. So the idea here, and I won't linger on it, is that like a huge amount of the effort that goes into like actual validation is this piece of it. So how do you make your simulator effectively look and act like the real world? Because if you don't do that, then any validation you get out of the simulator won't necessarily translate into that real world environment. Okay, so now let's talk about this third challenge, and I'll share a little bit more work from Sizzle, and that is the challenge of optimization. So now what we're going to say is that we have our objective locked down, we've modeled our environment, and we have a simulator set up. How do we actually like search for these failures in a way that is efficient, so that we actually find failures, and we find failures that have high likelihood, because that is the overall objective here. So one really cool example of a system that we looked at before is this system called TaxiNet. So TaxiNet is a very simple autonomous system, but it has some really good real-world impact. So the idea is that you would have an aircraft. It wants to sort of autonomously taxi around a runway so that it can sort of take off, go from airport to airport, and all autonomously. So the idea is that we'd have a camera on the wing of the aircraft that would be pointing down the runway, and our kind of main objective would be that the aircraft is able to kind of just taxi straight down the runway and like not go off on either side. And so the question that we asked was, can errors in the images that we get from the camera lead the aircraft to eventually find its way off the runway? Because that would be really concerning if that was the case. So to get a little more detail about what how the system actually operated, so we get in the sort of the high resolution image, we downsample it to a much smaller sort of low resolution image that's just in grayscale. And this is done so that we can have a very, very small neural network process that image and basically give us an estimate of where we are on the runway, so that we can then produce a control input that allows us to sort of stay straight and stay aligned with the runway as we go down it. And so this is operating in closed loops, which means that at every step we take in a new image, we downsample it, run it through the neural network, and then decide on a rudder control that allows us to stay straight. And the reason for wanting to have a very small neural network is so that we can apply some techniques that I'll talk about in a little bit in order to sort of verify the neural network and also do some stuff that I'll show you in a second. So if you actually just run this controller in a few different kind of environments, so this would be sort of your Monte Carlo sampling to evaluate how well the system behaves, then you get the following results. So like sort of no matter where you start on the runway, it's able to kind of determine where it's at and nicely kind of make its way to the center and then carry on straight. And then even when it gets some slightly different weather conditions, like it's overcast or something, you're able to still get really good performance. But as you should know now from this course, that does not mean that this system is necessarily safe, right? Just because we only ran a handful of simulations. Okay, so what's the idea here? The idea is we know that the camera is going to have some amount of noise, and that noise is maybe going to be roughly Gaussian distributed at each of the pixels. You kind of get that like fuzzy noise that can occur. And so the question is, what kind of noise might occur on the image that would lead the aircraft to have like a very incorrect steering angle one way or the other? So maybe it's like off to the right, it should steer to the left, but based on the noise it got, it actually is steering back to the right, which would be very bad. And so what we can do is say, okay, let's try to figure out what configuration of noise would lead to a maximum deviation at a single time step. And since our neural network is very small, we can actually use some tools from the neural verification literature, which we'll learn about in a few lectures or later on in the quarter. You can actually sort of solve this problem exactly. So you can say like, I want to maximize the error in my output based on the input noise, and we can figure out like what that little bit of noise would be to lead to that maximum error. And we can say, maximize the error to the right or to the left. So, okay, so then maybe what you do is say, all right, what if it got the worst possible error at every single time step? What would happen? So we say like, we are always biasing it to want to turn to the left, and it's already on the left side of the runway, so maybe it will just go off the runway. So when you do that, this is what happens. So what you're seeing here is on the bottom, the trajectory of the aircraft, the true image, the downsampled image, and then the perturbed image, which is getting this kind of noise applied to it that's causing the aircraft to sort of think that it's should be turning left. So we let this run for a while, and what we find is that we actually don't ever leave the runway. So we've just biased it every time to the left, but the network is sort of robust enough that it can understand, even in this sort of worst case scenario, that it's on the left side of the runway, and it should at very least not continue going left. And we end up with a safe trajectory, yeah.
So in this case, we're defining this worst case scenario. Are you saying then that the noise is bounded?
Yes, thank you. Yeah, so the question is the noise bounded? And yes, the noise is bounded to a certain level. So we're saying the noise can only go up to a certain threshold, and within that threshold, we're finding sort of the worst case scenario, yes.
How do you quantify worst in this case, and also how do you get it to be the left, like in particular?
Yeah, so the question is, how do you quantify worst, and then how do we sort of force it to be to the left or to the right? So we're quantifying worst based on we know what the control input should be, and then we want to say, like, we want to maximize the input to be the opposite direction. So if we know that it should be like to the right, the worst case for the left would be like it produces a steering control that actually like deviates it to the left. So it's that output piece.
Input image, which then pass through your entire controller and then define worst by the output.
That's correct, yeah. Cool, other questions, yeah?
Could you clarify how it knows to stay in, like, not to go past the
Yeah, so the question is, can I clarify how it sort of knows to not carry on off the runway? So what's going on here is that the neural network that is sort of controlling the output has been trained to basically predict where the aircraft is on the runway. And then the control kind of comes out of that, because if it's very far to the left, it'll kind of cause it to correct. So what's going on here is that even in the case where the aircraft is sort of off to the side and we're perturbing it adversarially, the neural network is robust enough that it has a pretty good estimate still of where we are on the neural network, or sorry, where we are on the runway. And because it has a pretty good estimate, then the resulting control means that at very least it's not going to kind of carry on over to the left. So it's just a function of the neural network actually being pretty good at what it was trained at. Cool. Yeah, love the questions. Okay, so that's what happens when we apply the same disturbance at all times. But as you should also know from this course, it really matters sort of the sequence of events that might occur, right? And so we can't conclude that this system is safe. So what the folks did here was to, again, apply Monte Carlo tree search to figure out at every step, I can either apply sort of the worst case disturbance to the left or to the right. And we're going to do this kind of like over time with the goal of trying to find failure outcomes. And we did this with different levels of, you asked about the bounding of the noise, so you can kind of change how much noise you allow for. And for example, at a 2% perturbation on the pixels, which is very, very small, we don't find any errors. So of course we can't conclude that there are no failures at all, but we don't see any. But when you bump that perturbation up to 3%, we start to see some really interesting things happen. So what's going on here is that the MCTS kind of algorithm found a failure trajectory where initially the aircraft was being biased to sort of drive to the left for a while. But then it gets out to a certain point and it switches. So it says now bias you to the right. And so the aircraft is actually already way off the runway, and now it turns and it's looking across the runway, and that image is sort of so outside of the training set, which only occurred, from casually, going down the runway, that it became really bad at the task of figuring out where it is, and it ultimately allowed the aircraft to kind of run off the runway. And you see other configurations here. Obviously, the more noise that we allow, it's sort of the easier it is to cause the system to fail, and you can find failure trajectories that are sort of shorter. This is one here where you are able to just sort of cause it to go to the left entirely. But this really drives home the point that you actually need to understand the sequence of events that could occur, because failures can emerge from really complex interactions. Yeah.
This is really cool. But also, when you start these type of like experiments, you don't go in knowing that you're going to find these things, right? So when do you know when to stop?
Yeah, that's a phenomenal question. So the question is, going into these experiments, you have no idea if there is a failure that you could find. So when do you know to sort of stop looking? And yeah, I think that's like a very, very difficult question, because it's very difficult to build a high enough degree of confidence that you say, like, I am certain that this system is safe to fly. I think Mykel could probably speak to this. So I think ACAS-X was in evaluation for 7-8 years prior to its deployment. So how did the FAA know that it was time to stop evaluating?
It's just gradual building of trust. There's no like well-defined termination condition.
Yeah.
Fundamentally, it can be like a needle in a haystack kind of problem where, I don't know, you utter some incantation and then suddenly the earth explodes, right? There's no way to prove that, that doesn't exist.
Yeah.
Right?
Yeah. So there is a way to prove the absence of failures, but it's not always so scalable, and you'll learn about that in the formal methods section. But yeah, it's a really great question, and it's very difficult to ever have full confidence that you found that you have proven that no failure exists. Yeah. Cool. Yeah.
I'm curious what the intention of, or I guess what the consequences of these results can mean for example, earlier we were trying to find most likely failures. In this case, now we have some bounded error. So I can imagine that what we say with these results are then we impose some constraint on the accuracy of our sensor.
Yeah.
Or I guess how else would you?
Yeah, that's great. So the question is broadly around how do you use these results and what they might mean maybe for the design of the system. And I think there's a spectrum of things of what it can mean. So you can take these results, treat them qualitatively. You can look at them and say, like, here's the behavior that we want to try to avoid in future versions of the system. You could take the result, I think, as your suggestion was, to be like, all right, at the 2% level of sensor noise, we seem to be okay, though again, we can never be fully confident. And so maybe we treat that as a specification on our sensor to say that, like, we can't allow for disturbances on the sensor that are larger than 2%. And you can use failure traces also to like train your model further. And there's lots of ways that you can kind of use these results.
Is there any case where we think about this in a probabilistic sense, like relating that error to some probability of failure? Or?
Yeah, so you might consider, and we'll talk about computing probabilities of failure, I think, in the next lecture or the lecture after. But yeah, you could imagine saying that, like, okay, for different levels of sensor noise, you can compute a probability that your system fails. And then you could say, okay, what are we comfortable with for failure probability? Yeah, lots of ways you can slice it. Yeah.
Maybe for this example, creating a probabilistic model of noise in the sensors is just really kind of very difficult, right? Because it's you have a lot of latent variables and so forth, and so this is basically giving an epsilon ball kind of worst case noise model. And that's really just a proxy for what we would really love, which is a probabilistic model, but that's too hard to make.
Wonderful. Okay, so let's carry on. So the last thing I want to talk about today is just sort of like, what are the kind of latest things that are happening in this domain? And if you were interested in doing like some research on this topic, number one, who you should do it with, but also number two, what are the things that are kind of still open? So this is some work that Harrison's been working on. Using diffusion models, which are a type of deep generative model that have seen like a lot of success over the past couple of years. These are the models that underlie things like stable diffusion or DALL-E, like the image generation type stuff. And they're really good at representing very complex distributions. And so one use case of very complex distributions is finding interesting failures of really high dimensional autonomous systems. And so that's the idea that Harrison was working on. So diffusion models have been used in a bunch of different domains. So as I said, initially, these were sort of like used for image generation tasks, similar to GANs or VAEs. But then people quickly realized that you could also kind of treat things like robotic planning as a high dimensional kind of distribution matching task, where you might say you have your robot arm in a particular location, you have a target goal, and you want to learn sort of the path that the robot should take in order to reach that goal. And you can produce a bunch of training data by basically having a bunch of random configurations of where the arm is. It moves to some place and say, well, imagine I wanted to get to that place. Here's what the path would have looked like. And you can use that to sort of train a diffusion model that is conditioned on the start and end, and it will produce a trajectory. So that could start sounding a little bit like what we might want to do for failure discovery, where the objective is, you're in an initial state and you want to have sort of a potential failure outcome. We just need to think of a way to produce that data. So that's what Harrison was thinking about. Can we use these types of sort of conditional diffusion models to sample diverse and likely failure modes? Okay, so the algorithm that came out of this, called diffs, or diffusion-based failure sampling, the idea was that we would basically, because failures are rare, we can't just generate a bunch of samples where we have initial states and failures. So instead, what we're going to say is we're going to define some risk metric. This is sort of like that miss distance that we talked about at the beginning here, where the two aircraft, how close they got together, as sort of a proxy for how close we are to failure. So we're going to call that R, and that's going to be our risk measure. And what we can do is we can run a bunch of random samples. We can compute the risk metric of those samples. Maybe all of them are still far away from failure, but nonetheless, there's some distribution of risk that we would get from these samples. And we'll turn that into a data set. And then we can train a diffusion model on that data set so that we can produce posterior samples of our disturbances conditioned on a particular risk measure. Now, this diffusion model is only going to be good around the sort of risk measures that we've showed it, but we should be able to produce additional disturbance samples with a particular risk. And so we can sample some more disturbances. But then what we might want to do is update the risk threshold. So now we're going to up the level of risk that we want to see, produce more samples there, and then retrain the model to be more effective in the higher risk areas. And so we can iterate this process and ultimately try to produce samples that lead to failure. Yeah.
When you say you update the threshold and produce more samples, are these samples from the diffusion model or from rolling out?
From the diffusion model.
I see. So it's sort of bootstrapping.
Yeah, so the disturbance samples are from the diffusion model. You then run them through the simulator, and then you get the risk out. Yeah, so to walk through this a little more slowly, we're going to define a toy problem here. So the idea is that we imagine that our disturbances are coming from a 2D Gaussian, so it'd be centered at this 0, 0 mark, and you get some samples in the center. And then we'll say that a failure occurs if one of those samples lands in one of these boxes in the top left or top right. And then our risk measure is going to be sort of like just the distance to one of those failure regions. And we'll say a failure occurs when our risk level is greater than 3. And that's what the red boxes define. So the first step is we just produce some samples from our original unit Gaussian distribution, and indeed none of them kind of hit our very rare failure modes, but we have a pretty good spread of the different risk that's associated with each sample. So we can train our diffusion model on it, and in particular, we're training on these sort of pairs of what the risk is and what the disturbance is. And then what we can say is, all right, we're going to then take we're going to create new samples of our disturbances that are sampled from risks between uniformly sampled at higher levels of our risk threshold. So we'll produce those samples and then evaluate the risk of each one. And on that second iteration, we get more samples in the higher risk zones. And we can see those there, and then we can add those to our data set, create a new risk threshold to take the upper quantile of those, and just continue repeating on this process until we've basically, and we combine it with the other data, but we repeat this process until we're getting closer and closer to that failure distribution. And we iterate on this until our sort of movable risk threshold matches the failure distribution that we care about. And we ultimately end up with samples that look something like this. And you can compare this down to the little plot that's on the left here. These are samples from the actual failure distribution that Harrison produced by just running lots and lots and lots of Monte Carlo simulations. So the results are pretty cool, but you might say, okay, this is just a simple toy problem that's meant to be visual. But Harrison's done this on a bunch of other problems. So these are trajectories that might look a little bit familiar from the inverted pendulum problem, where the disturbances are kind of on the torque of the pendulum. And what you're visualizing here is sort of steps in that sequence of diffusion modeling process, where over time it is getting better and better at producing failures that look a lot like the most likely failures of the system. Another really cool example comes from the F-16 model, which I understand some of you might be working on for the final project. So this is a very high dimensional model with many degrees of freedom that's operating over time. And this diffs model is able to find these sort of higher likelihood failure modes where the aircraft actually comes into contact with the ground at the tip of that trajectory. So it's actually like these types of problems are extremely difficult to solve with traditional optimizers because of the high dimensionality, and doing this sort of combined data-driven iterative approach has been surprisingly effective. So that's at a really high level. You should definitely talk to Harrison to learn more about what he's doing with that work, as well as some follow-on works that I think are going on as well. Okay, so I think the very last thing I want to say before we wrap up the transportation systems piece, this is something that I'm sure Sydney has talked about, but and as Mykel just mentioned, safety is really something that is very holistic. From how you think about the requirements of your system to how you design it, how you test it, and how do you ultimately kind of decide whether or not it's ready to be out in the world. And adaptive stress testing just represents one very small piece of the puzzle here, where it allows us to sort of automate a laborious part of this cycle, which is to discover those edge cases or the interesting outcomes or failure modes that we can't really find by just thinking about it. But then that has to kind of cycle back into the whole process in order to ultimately end up with a product that we feel comfortable releasing out into the world. Okay, so let me pause there and see what questions you have, and then I will jump a little bit into the work that I've been working on at Terra AI and on these Earth resource problems. Yeah.
Do you want to say something about transfer learning?
Sure. Yeah, that's a really great question. So the one other problem here is that because it's very labor intensive to generate these failure cases for a particular system. So maybe you've designed your system and then you spent, 10 weeks of, a huge server farm running simulations, and you're really, really happy with the results, but you found one or two things that you'd maybe like to tweak. So you go back and you update your system. All of the safety validation that you just did becomes basically irrelevant now, right? Your system has changed, and so you can't really trust the outcomes because you don't really know, especially in this day and age, what those small changes that you just did might, what outcomes they might have. So some other work that's come out of the lab and some things that I've worked on are related to transfer learning. So maybe you can't take those validation results and just trust them wholesale on the new system, but maybe you can use them to sort of warm start the validation process on another iteration of your system that might be better or have different failure modes or whatever. And this can kind of like dramatically reduce the amount of time you're spending searching for failure modes by kind of leveraging what you already know are maybe difficult scenarios for these types of systems. So I think that's also a very exciting kind of direction for future research. Cool. So we got about 15 minutes left. I'll go through this part pretty quickly, and then happy to take questions afterward or offline as well. Okay, so I want to talk a little bit about what got me interested. So I was working a lot on sort of autonomous driving, aviation, and when I started encountering these problems in sort of the climate space, I became really hooked, in part because I think they're really deeply interesting problems, but also they have a really important impact. So right now, we are at a really, really big inflection point in terms of what could or could not occur with the climate crisis. So this is sort of showing, a variety of possible heating outcomes that could occur with different types of policies that might be enacted. So we have in orange here, like the current set of policies, which may or may not sort of hold up now, or may or may not have been followed. If we do nothing, we're in a very, very serious situation here with more than 4 degrees heating. But there are even pathways down to things that only lock in temperature increase of around 1.5 to 2 degrees C, which is still very, very bad, but it's a lot better than what could be. So I think it's just super important that a lot of good technology and policy comes online right now in order for us to address this problem going forward. But there are a lot of open issues. So number one, the demand for energy is just increasing. So as the rest of the world is developing, and in fact, even in the more developed world, the amount of energy that each person consumes is just going up. And, some amount of changing of behavior is likely to be necessary here, but we can't necessarily ask the rest of the world to not develop, for example. And so we need ways of basically dramatically upping the amount of energy that we produce, as well as reduce our CO2 emissions if we're going to hit these goals. And so it's going to be kind of a suite of technologies that do this. So you can see here the change of behavior, the energy efficiency, electrification, and then correspondingly renewable energies. And then things like carbon storage, where certain things that are hard to decarbonize, like the production of cement or fertilizer or air travel, we need a way of sort of taking CO2 and keeping it from going into the atmosphere. Additionally, there's projected to be a huge shortfall in the amount of critical minerals that we need for the development, so the electrification of all of the grid, as well as the need for all these different batteries and all the electronics that we need. Basically, there's a huge lack of minerals that we need to pull out of the ground. And yet we seem to be getting worse and worse at finding new mineral deposits. So what you see here is basically how many new discoveries have been made recently. And you can see that there's like a trend downwards, despite the yellow curve, which is the amount of exploration investment that's been done, is going up. So people are spending more money to try to find things, and they're getting worse and worse at finding it. And the explanation for this is pretty simple. It's that all the easy stuff has been found. And so we need to look deeper and find sort of more complex systems in order to find the minerals that we need. So all of this is to say that the subsurface is a really key resource. So historically, it's been a key resource because it's where we got hydrocarbons and pulled them out of the ground. But now it's also going to be a key resource for the net zero transition. So I showed this sort of slide already, but we have the raw materials, we have renewable energy, and we have carbon storage. So what's interesting about these problems is that although they are extremely different from one another, the development of new energy systems, the storage of carbon, they actually have one sort of commonality to them, which is that you need to make very complex decisions in highly uncertain environments. And again, that uncertainty comes from the variability in the geology of what could be underneath the Earth. So let me talk about what that problem looks like in the setup of a carbon storage problem. So in carbon storage, we are basically drilling deep into the ground, into these typically saline aquifers. So it's like this porous rock that has salt water in it, so it's not that useful for drinking. And usually that rock is sort of capped by a harder rock so that you can inject CO2, which wants to float its way back to the surface, but it will remain trapped like an inverted bowl underneath the ground. And our goal is to basically inject as much CO2 as we can and keep it trapped there. So if that CO2 does find its way back to the surface, that can be a very bad thing. I'll talk more about that in a second. But the trick here is that we don't actually know what this thing that we're injecting into, what it actually looks like. So what we can do is we can maybe drill an exploration hole. We can observe sort of like at a particular point, what are the properties of the rock. We may also when we're operating the reservoir, so we've drilled a hole, we can sort of put a sensor down there and observe what's going on at that particular position. Or we can do things like take measurements from the ground, like seismic measurements, which is basically like an ultrasound, but for the Earth's subsurface. So you can get some measurements of the rock density and stuff like that. But all of this paints a very, very incomplete picture of what's going on there. And why this matters is if we're uncertain about what the subsurface looks like, we can't really answer questions about where we should inject into it because there are better and worse places for the ability to inject CO2. We can't answer basic questions like how much CO2 will we be able to inject? And that's important from a business perspective when you need to sort of sign contracts saying I will store X amount of CO2. And then if we do want to try to learn more about the system, what types of measurements should we take? Should we go take seismic measurements? Should we go drill into the ground? In what order should we do those measurements? And what's really cool about this problem, in my opinion, so for those of you who have taken Mykel's other courses around decision-making under uncertainty, is that you can formulate this problem as a POMDP. So it's partially observed because we don't know what the state of the subsurface is, and yet you're taking actions and you have objectives and constraints. And then what we can do is we can throw sort of like our various POMDP solvers at it, and we can do Bayesian inference when we get new sources of data. How do we update our belief about the subsurface? Some of the other things that we work on are one thing a POMDP always has is a transition function, which describes sort of how the system will evolve over time. So in the case of carbon storage, we're injecting CO2 into the ground, and then it is migrating underground over time. And we need to make sure, again, that this CO2 is being trapped for like thousands of years, or until it actually like solidifies and turns into salt, basically. And so we need to be able to simulate that process. And historically, people have spent a lot of effort building building these sort of physics-based simulators of how gas would evolve underground. But they're super, super slow. So running one simulation would take us maybe like 10 or 12 hours. And if we want to do any sort of like AI or optimization, we need to be able to do that much, much faster. So some of the work that we focus on, both in research and at the company, is building surrogate models for this type of process. So what we do here, it's a purely supervised learning task. We run some physics-based simulator to produce, what would the CO2 plume look like underground? How would it evolve? And then we train a deep neural network to just imitate that physical behavior. And we just do it on a bunch of diverse samples. And what you get out is basically a simulator that is thousands of times faster. And it's a little less accurate, but it sort of more than makes up for that lack of accuracy by being able to consider way more sort of scenarios of what could occur. Okay, and the result of this, and this is a paper that's in submission right now, is that sort of a POMDP solution that was done using a basic optimizer is able to do better than the human reservoir engineers who are being sort of tasked to design these reservoirs. So what we're showing here basically is the design of the reservoir, so where they put the injectors, they inject CO2, and then that CO2 sort of evolves over roughly a 1,000-year period. And then we can measure, in this simulation, how much of the CO2 sort of remained trapped in the reservoir, or how much of it exited the domain, and therefore could potentially leak back up to the surface. And in the case of the sort of reservoir engineering expert, they still had situations where like 16% of the CO2 leaked out of this volume, whereas the AI was able to do it with a very, very small leakage fraction. So this sort of shows the potential of applying these sort of algorithmic decision-making tools to this problem. Now let me talk about some of the risks, and this is why these problems are safety critical. So number one, this is a risk that's probably most associated with the production of geothermal energy, but it's also associated with carbon storage. And that is the risk of induced seismicity. So in geothermal energy, typically what you're doing is you drill 2 holes in the ground, you pump cold water into one, and you extract hot water from the other one. And sometimes when they're injecting water into the ground, they are injecting it at really high pressures so that you can get like a lot of throughput of water and therefore pull a lot of heat out of the ground. But when you do that at high pressures, you can basically reactivate faults that are in the area. So faults are, these sort of breaks in the subsurface that are typically under some sort of stress state. And when they slip, that's what causes earthquakes. And so there's even been earthquakes that have been caused by geothermal sites. So there was a huge earthquake in South Korea that they ultimately tied to a geothermal plant that was just outside the city. And because geothermal is used to produce electricity and heat, they're often nearby cities. And so therefore these types of disasters can really harm people. Another potential issue, so going back to the carbon storage case, is when you pump a bunch of CO2 under the ground, as I described, it wants to find its way back. So if it can find a fault or something, it will begin to kind of migrate back to the surface and can potentially, in the best case, it'll just go back out into the atmosphere and it kind of defeats the whole purpose of what we were doing. But in the worst case, it can actually kill people. So this is not a carbon storage case, but it is a naturally occurring thing that occurred in 1986. There was a lake, there was a huge amount of CO2 trapped like geologically under this lake that for whatever reason all came out in one big plume, and it actually suffocated a local village and a bunch of livestock. So this is an extremely dangerous thing. Ideally we do this type of operation offshore where there aren't people around, but there are projects that are being discussed for onshore operation as well. And so these are some of the really important things that we need to focus on. And yet we're in this situation where we have a lot of uncertainty in our state. We have very complex transition dynamics, and we have very limited observations of how we might operate. And so some of the work that I think Sizzle will be doing over the next few years and that we will be doing at the company is how do we actually do the safety evaluation for these more automated decision-making agents that are going to be thinking about how to solve these problems. So let me pause there for a second and also welcome you guys to share with me now or in the future, like what your ideas are. How would you tackle this as a safety evaluation problem based on what you learned here in the class or what you learned for the remainder of the course? So any thoughts? Actually, I would love to hear like how would you apply some of the techniques that you have been learning about.
Question, actually.
Yeah.
How does the observations look like with these scenarios? Because I guess, like, do you have enough to make conclusions on?
Yeah, so what do the observations look like? So the observations are very diverse. So there's these like big surveys, seismic surveys, geophysical surveys, and then there are these kind of localized point measurements. And yeah, the observations do constrain what could be in the subsurface, but typically part of this whole process is encouraging these companies to do additional data collection in order to better understand the reservoir before operating these projects. So it's kind of, it varies a lot. Yeah, question?
Yeah, so to answer your previous question, well, not to answer it, but like to say, I feel like the first half of the talk was very focused on sort of optimizing some disturbance, whereas the second half of the talk is sort of like, let's watch what happens and see what happens.
Yeah.
And I'm curious if there's opportunities to sort of apply disturbances in the shape of like, these are some Earth events or whatever. I'm not sure what the right term is for that. And sort of in a more active way search for failures in these cases.
Yeah, that's great. So the idea being, can we take some of the more active searching of failures to these types of problems? So indeed, I think probably one of the biggest drivers of outcomes here is the geological uncertainty. And so you could look for specific geological instances, let's say, that would lead to some adverse outcome. And then maybe you go do some data collection to look for those in particular. So I know we're coming up on time, so we can chat more after this. Just want to do a quick plug. There is sort of a simplified CO2 injection POMDP that we did for a NeurIPS workshop paper a couple years ago. So you'd be welcome to work on this, either for this project or in the future. Feel free to reach out if you have questions about it. And then one other thing, if you are an undergraduate, we are doing internships funded by the Tomcat Center here at Stanford for this summer, if you're interested in thinking about these types of problems in an intern fashion. But thank you all so much. Feel free to reach out to me with questions, and it was a pleasure chatting with you all.